You think you know why things fall. Drop something, it falls down. Let go of a ball, it hits the ground. Gravity pulls it. Simple. Everyone knows this. You learned it before you could read. Things fall because gravity pulls them down. But here's a question. What is down? Point to it. Right now. Point in the direction of down. You're pointing at the floor or at your feet. You think down is a direction, like north or left. You think it's an absolute thing, a fixed direction in space. And that's your first mistake. That's where your understanding breaks. Ask someone in Australia to point down. They point at their feet. Ask someone in New York to point down. They point at their feet. But those two people are pointing in opposite directions. Opposite. If down is a direction, how can it point both ways? How can two people on opposite sides of the planet both be pointing down when they're pointing at each other? You say, well, down means toward the earth. Fine. But why toward the earth? Why not away from it? What makes toward special? You're just relabeling the mystery. You're saying things fall down because down means the direction things fall. That's circular. That's not an explanation. That's just words chasing each other around the track. Let me push harder. You're standing on Earth. You drop a ball. It falls toward the center of the Earth. But the Earth is a sphere. There is no down on a sphere. There's no up either. There's only toward the center and away from the center. Every direction on a sphere is equivalent. North, south, east, west, they're all horizontal. They all circle the globe. The only special directions are radial, toward the center, away from the center. So when you drop that ball, it's not falling down, it's falling inward, toward the center of the earth. And here's the question that's going to break your brain. What's pulling it there? You'll say gravity. Fine. What's gravity? You say it's a force. Okay. What's applying that force? What's reaching out from the earth and grabbing the ball and pulling it down? Show me the rope. Show me the mechanism. There's nothing touching the ball. It's surrounded by air, empty space. There's no physical connection to the earth. So what's pulling? You can't answer that, can you? Because you don't know what gravity is. Nobody taught you. They taught you the word. They taught you the equation, maybe. F equals ma, or F equals gmm over r squared. But they never told you what gravity actually is. They gave you a description. They didn't give you an explanation. And here's what's going to make you uncomfortable. When you really dig into it, when you really ask what's happening when something falls, you discover that nothing is pulling. There is no force in the way you think of forces. Gravity is not a pull. It's not a push. It's not a rope or a hand or a field reaching out and grabbing things. Gravity is geometry. Let me show you what that means. But first, we need to destroy your intuition completely. We need to make you see just how broken your everyday understanding is. You're sitting in a chair right now. You feel the chair pushing up on you. You feel your weight pressing down. You think you understand this. The earth pushes you down with gravity. The chair pushes you up with normal force. The force is balance. You don't move. Equilibrium. Wrong. Stand up. Jump. You leave the ground. You go up. You come back down. While you're in the air, nothing is touching you. The air doesn't count. It's not supporting you. You're in free fall. You're accelerating downward at 9.8 meters per second squared. That's what we measure. That's what we call gravity. But here's the thing that should shatter everything. When you're in free fall, when you're falling through the air with nothing touching you, you feel weightless. Jump off a diving board. For that brief moment before you hit the water, you feel nothing. No force, no pull. Your stomach doesn't feel pulled down. You don't feel stretched or compressed. You feel exactly the same as you would floating in empty space, far from any planet. Astronauts in orbit are in free fall. They're falling around the Earth constantly, and they feel nothing, weightless, no sensation of being pulled. They're accelerating, falling at enormous speeds, and they feel nothing. But when you're sitting in your chair, when you're standing on the ground, you feel weight, you feel pressure, you feel a force. Stop, think about this. When nothing is touching you, when you're in free fall, accelerating at 9.8 meters per second squared, you feel nothing. But when something is touching you, when the ground is pushing up on you, preventing you from falling, you feel weight, you feel force. That's backwards. That's completely backwards from what you think is happening. You think the earth is pulling you down and the ground is pushing you up and those forces balance. But if that were true, you'd feel the pull when you're falling. You'd feel stretched. You'd feel the earth tugging on you. But you don't. You feel nothing when you fall. You only feel forces when something stops you from falling. When the ground gets in your way. When the chair blocks your natural motion. That's when you feel weight. That's when you feel force. Gravity is not a force, not in the way you think. Let me come at this from a different direction. Imagine you're in an elevator. The cable snaps. The elevator falls. You're inside falling with it, and you float, weightless. You and the elevator are both in free fall, both accelerating at the same rate. So relative to the elevator, you're stationary. You drift. No weight, no pull. Now imagine you're in a rocket in deep space, far from any planet, far from any gravity. The rocket fires its engines. It accelerates upward at 9.8 meters per second squared. You're inside. You feel weight. You're pressed against the floor. It feels exactly like standing on Earth. Exactly. There is no experiment you can do inside that rocket to tell whether you're accelerating in space or standing still on Earth. Einstein realized this. He called it the equivalence principle. Acceleration and gravity are indistinguishable, not similar, indistinguishable. There is no local experiment that can tell them apart. And this reveals something profound. When you're standing on the ground, you're not in equilibrium. You're accelerating. The ground is pushing up on you, accelerating you upward, and you feel that acceleration as weight. But you're not moving upward, you're standing still, so what are you accelerating relative to? You're accelerating relative to free fall. Free fall is the natural state. It's what happens when nothing interferes. You're standing on the ground, and the ground is in your way. It's preventing you from following your natural path, which is to fall. The ground pushes up, you accelerate upward relative to the natural falling path. You feel that acceleration as weight. When you jump, when you enter free fall, you stop accelerating. You follow the natural path. No forces, weightless. That's the state of no forces. Falling, not standing. Your intuition is inverted. When you think falling requires a force pulling you down, you think standing still requires forces to balance. But it's the opposite. Falling is what happens when there are no forces. Standing still requires a force, the ground pushing up, accelerating you away from the natural path. Now, what is that natural path? Why do things fall toward the earth in the first place if nothing is pulling them? This is where Einstein's insight becomes beautiful and terrifying. The natural path is a straight line through space-time. Not space, space-time. You think space and time are separate. You think you move through space while time ticks along separately. But they're not separate. They're woven together. Space-time. One thing. And the presence of mass warps that fabric. Imagine a trampoline. Stretch it flat. Roll a marble across it. The marble goes in a straight line. Now put a bowling ball in the center. The trampoline sags. The fabric curves. Now roll the marble again. It doesn't go straight anymore. It curves toward the bowling ball. Not because the bowling ball is pulling it, but because the surface is curved. The marble is still following the straightest possible path, a geodesic, but the surface is bent, so the path curves. Space-time is like that trampoline. The Earth is like the bowling ball. Its mass curves the space-time around it. And when you drop a ball, when you let it enter free fall, it follows the straightest possible path through that curved space-time. That path, that geodesic, curves toward the Earth. The ball falls. But nothing is pulling it. The ball is just going straight. It's space-time that's bent. You want a force? There is no force. You want something pulling? Nothing is pulling. The ball is doing what everything does when left alone, moving along a geodesic. And the geodesic curves because the geometry is curved. Gravity is not a force. Gravity is the curvature of space-time. When you're standing on the ground, you're trying to follow that curved geodesic. You're trying to fall toward the center of the Earth. But the ground is in the way. The electromagnetic forces between the atoms in your feet and the atoms in the ground resist. They push up. That push accelerates you away from the geodesic. You feel that acceleration as weight. When you jump, when you remove that resistance, you're free. You follow the geodesic. No forces act on you. That's why you feel weightless. You're not being pulled down. You're going straight through curved space-time. This is not a metaphor. This is not an analogy. This is what's actually happening. Einstein's equations, the Einstein field equations, describe precisely how mass curves space-time, and the curvature they predict matches every measurement we've ever made. The orbit of Mercury, the bending of starlight around the sun, the gravitational waves from colliding black holes, all of it matches exactly. Space-time is curved. That's not a model. That's reality. Now let's go deeper. Let's ask why mass curves space-time. What's the mechanism? How does a chunk of matter reach out and bend the geometry of space and time? And here's where we hit the limit. We don't know. We can describe it mathematically. Einstein's equations tell us exactly how much curvature a given mass produces. We can calculate it, we can predict it, we can measure it, but we can't explain why the equations work. We can't reduce them to something simpler. Mass curves space-time because that's what mass does. It's a fundamental property. Just like electric charge creates electromagnetic fields, mass creates space-time curvature. That's the rule. That's what we measure. You can ask why charge creates fields. You can ask why mass curves geometry. But those questions don't have answers in the sense you want. The universe has fundamental properties: charge, mass, spin. And those properties behave in specific ways. Charge creates fields. Mass curves space-time. Those are the bottom-level rules. Physics doesn't tell you why the rules exist. Physics tells you what the rules are and how to use them. And the rule for gravity is this: mass tells space-time how to curve, and space-time tells matter how to move. That's it. That's the complete description. But let me show you why this is beautiful. Let me show you how much this explains. The planets orbit the sun. Why? Not because the sun is pulling them, because the sun's mass curves space-time, and the planets follow geodesics through that curved space-time. Those geodesics are ellipses. The orbits emerge naturally from the geometry. The moon orbits Earth. Why? Same reason. Curved space-time, geodesic motion. GPS satellites have to account for time dilation. Why? Because space-time isn't just curved in space, it's curved in time. Clocks at different heights run at different rates. The curvature affects time itself. If we didn't correct for this, GPS would be off by miles within hours. Light bends around massive objects. Why? Because light follows geodesics too. When starlight passes near the sun, it bends. We see stars in slightly wrong positions during a solar eclipse. That's space-time curvature. Arthur Eddington measured this in 1919 and confirmed Einstein's predictions. Gravitational waves exist. When massive objects accelerate, they create ripples in space-time. Those ripples propagate outward at the speed of light. We've detected them. LIGO, the Laser Interferometer Gravitational Wave Observatory, measured gravitational waves from colliding black holes. The signal matched Einstein's predictions exactly. All of this, orbits, time dilation, light bending, gravitational waves, it all follows from one idea. Space-time is curved by mass. That's it. One principle explains everything. And here's what should blow your mind. Newton knew none of this. Newton thought gravity was a force. He thought objects pulled on each other through empty space. He gave us equations, F equals gmm over r squared. And those equations worked. They predicted planetary motion. They explained tides. They let us calculate orbits and launch satellites. But Newton himself said he couldn't explain what gravity was. He said, "I frame no hypotheses." He gave the description, not the explanation. The force law worked, but he didn't know why. Einstein figured out why. 230 years after Newton, Einstein realized gravity isn't a force at all. It's geometry. And suddenly, everything Newton observed, all the orbits and motions and accelerations, they all fell out naturally from curved space-time. That's how science works. Newton gave us the how. Einstein gave us the why. Not the ultimate why, we never get that, but a deeper level of description, a unification. What looked like a mysterious force pulling objects together is actually objects moving naturally through curved geometry. And we tested it over and over. We measured the orbit of Mercury. Newton's equations predicted a certain precession, a slow rotation of the orbit, but the measurements didn't match. There was a tiny discrepancy, 43 arc seconds per century. Tiny, but real. Newton's theory couldn't explain it. Einstein's theory could. When you calculate Mercury's orbit using curved space-time instead of Newtonian force, you get the extra 43 arc seconds exactly. The discrepancy vanishes. The theory works. We measured light bending. Einstein predicted starlight should bend by a specific amount when passing near the sun. Eddington measured it during the 1919 solar eclipse. The deflection matched Einstein's prediction. The newspapers called it the greatest scientific discovery in history. We built GPS. We put atomic clocks in orbit. We measured the time dilation. Clocks in orbit run faster than clocks on the ground because they're in weaker gravity, less space-time curvature. The effect is tiny, microseconds per day, but it adds up. If we didn't correct for it, GPS would fail. We detected gravitational waves. On September 14th, 2015, LIGO detected a signal. Two black holes, each about 30 times the mass of the sun, spiraled together and merged. The collision released energy, converted 3 solar masses worth of matter into energy in a fraction of a second. That energy radiated away as gravitational waves, ripples in space-time. Those ripples traveled for 1.3 billion years across the universe. They reached Earth. They stretched and squeezed space-time by a tiny amount, less than 1,000th the width of a proton, and remeasured it. The signal matched Einstein's predictions exactly. The frequency, the amplitude, the decay, everything. Einstein wrote the equations in 1915. We confirmed them in 2015. 100 years later, the theory works. So when you ask why things fall, here's the answer. Things fall because they're following straight paths through curved space-time. The Earth curves space-time around it. Objects near the Earth follow geodesics through that curved geometry. Those geodesics accelerate toward the Earth's center. We call that acceleration gravity. But it's not a force pulling, it's geometry guiding. Down is not a direction. Down is the local curvature of space-time. It's the direction the geodesics point, and that direction is different everywhere. In New York, geodesics point toward New York's ground. In Australia, geodesics point toward Australia's ground. Both directions are down because down means along the geodesic, and geodesics point toward mass. You're not being pushed to the ground. The ground is pushing you away from your natural path. Your natural path is to fall, to follow the curvature. The ground interrupts that path. The electromagnetic repulsion between atoms in your feet and atoms in the earth pushes up, accelerating you away from the geodesic. You feel that acceleration is weight. Remove the ground, jump off a cliff, and you're free. You follow the geodesic, weightless. That's the state of no forces, falling. And it feels like nothing, because you're just going straight through curved space-time. This is what gravity is. Not a mysterious force reaching through space and pulling objects together, but the natural consequence of mass curving the geometry of space-time, and objects following the straightest paths through that curved geometry. And here's the beautiful part. You experience this every second of your life. Every time you feel weight, you're feeling the ground pushing you away from a geodesic. Every time you drop something, you're watching it follow curved space-time. Every time you look at the moon, you're seeing an object tracing an ellipse through curved geometry. Gravity is not a force acting on you. Gravity is the shape of the universe around you, and you move through that shape, following its contours, tracing geodesics, obeying geometry. You thought falling required a force. You thought standing still was natural, but you had it backwards. Falling is natural. It's what happens when geometry guides you and nothing interferes. Standing still requires a force, the electromagnetic resistance of the ground, pushing you away from that natural path. The universe is curved. That's not a metaphor. The geometry of space-time is non-Euclidean. Parallel lines converge. Straight paths curve. And you, right now, sitting or standing, you're experiencing that curvature. The weight you feel is the ground accelerating you away from the natural geodesic that your mass wants to follow. You're not separate from this geometry. You're part of it. Your mass contributes to the curvature. You bend space-time too, just a tiny amount, too small to measure directly, but it's there. Everything with mass curves space-time. The Earth, the sun, you, a grain of sand, we're all embedded in this dynamic, curved, four-dimensional geometry, all warping it, all responding to it, all following geodesics through it. That's what gravity is. That's what falling is. That's what down means. Not a direction, not a force, but the curvature of reality itself. And the fact that we can measure this, that we can test it, that we can detect gravitational waves from black holes colliding 1 billion light years away,